Hello guys, welcome back. So what we're going to be talking about today is reaction rates. So reaction rates are a study of how fast a process occurs, which we might need to know if we need to do this in an industrial setting, that kind of thing. So we'll talk about the rate at which these happen. But before we get started, we always have to do a review first. So I'm going to move this out of the way and talk to you about and it might help if I actually share what I'm trying to show you. So let me share this screen. There we go. And this is the review that we're going to be talking about. Now, you'll notice they have 0.88 volts written down here. We're going to need that in this slide. I had to Google it to be able to use this. I don't know why I didn't put it on the slide, because it should have been there because it's not in the tables that you guys get for the test. But that's okay. If you don't have it in one of your resources, that does mean that you can Google it to find it, or you can ask me about it, that kind of thing. It should be given to you. There is no way that you're supposed to know what that value is, not at this point. I've been asked to draw a voltaic cell for the following reaction. Zn plus NO3 minus goes to Zn2 plus NH3 or NH4 plus. So I have two half reactions. I need to pull these two things apart. And so when I do that, I have a Zn going to a Zn2 plus, and of course I'm going to need 2 electrons there, and then I'm going to have an NO3 minus going to an NH4 plus. And I can't just add electrons to that, and there's a reason, because it's not balanced yet. So I need to take that portion one and find some space. Sorry. NO3 minus is going to go to NH4 plus. Now I have one nitrogen on both sides, so that part is balanced. So I need to deal with the oxygen. I have an excess of oxygen on my reactant side. I have 3 of them. I don't have any on my product side, so I need to add 3 H2O to even that out. Then I have to deal with the hydrogen, so I just added 6 more hydrogen to my product side, and I already had 4. So I need to now add 10 H plus to the reactant side, to the NO3 minus. That gives me my NH4 plus 3 H2O. If I look at my charges here, I see that I have a 10 plus 10 minus 1. That gives me a net of 9 plus. And of course, this one right here is plus 1, so I need to add 8 electrons to the reactant side to make that work. So I'm going to have 8E minus plus 10H plus an NO3 minus goes to NH4 plus 3H2O. And that's my charge. So just double checking this, I see that I have 1 nitrogen. I have 10 hydrogens on my reactant side, and I have the 4 from the NH4, and then, 6 from the H2O, so that's a total of 10. I have 3 oxygens on my product side, I have 3 on my reactant side, and of course my net charge on the product side is plus 1. My net charge on the reactant side is also plus 1, because we have our 8, which is negative, plus the 10, that leaves me with plus 2, but we have the NO3, so that's 1 more, so it's just plus 1. Okay, so I've summed those up. So that's the half reaction for that. Now, I've been asked to draw a voltaic cell. Okay, voltaic cells require 2 things, or a couple of things. 2 beakers. Those beakers both have to contain solutions. They have to be connected by a salt bridge, otherwise we won't have electrical neutrality, and therefore that isn't going to work. So that's my salt bridge. I also know that I'm going to have some sort of metal as an electrode here that's connected to a voltmeter, which is also connected to some sort of electrode over here. We don't yet know what those electrodes are made out of. We'll get to that in a few minutes. Now, let's talk about this. In this first half reaction, I lose the electrons. So lose electrons oxidize. So that's my oxidation. Down here, this is a gain electrons reduce. Now, when we talked about drawing voltaic cells, we said that the convention was to put the anode, where the oxidation occurs, on the left. Remember, Leo on the left. So I'm going to put my Leo over here. And that means that this is my, and of course, I just said, this is then the anode. This then is where my reduction occurs. This is the cathode. Since this is the oxidation, it's where the reducing agent is, because it causes reduction in something else. So reducing agent. And not all of these are questions that I got asked. I'm just running through everything that I remember talking about yesterday. This is then an oxidizing agent. I know that my electrons leave from here, go through this path over here, down that way. Okay, so that's the direction of my electron flow. This right here is a Zn going to Zn2 plus 2 electrons. This one over here is the 8e minus plus 10h plus NO3 minus going to NH4 plus 3H2O. Now, zinc is a solid, so that is the electrode that I have present here, and that means that the Zn2 plus is in my solution. Okay. Really messy, really ugly, I understand. Over here, I know that in this beaker, so right in here, I have NO3 minus and NH4 plus, because they're both ions, so they have to exist in there. And that means the material that is here in this electrode is platinum. Okay? So that's my platinum electrode. Whoa, awesome. That was fun. I think that's everything that I need to put on there, can put on there, whatever. What is the cell potential for this reaction? Well, the Zn to Zn going to Zn2 plus 2 electrons is an oxidation. The reduction of Zn2 plus 2 electrons going to Zn solid as an standard reduction potential of negative 0.76. So the E naught reduction for this reaction equals negative 0.76. The E naught for this, E naught reduction, equals 0.88 volts. And that means that when I calculate my E for the cell, and it's a standard still because I haven't changed anything, that it's going to be the E naught reduction at the cathode minus the E naught reduction at the anode, which is equal to 0.88 volts minus the negative 0.76 volts. And that should give me an answer of 1.64. So that's my standard reduction potential. Okay, awesome. I couldn't do that. If the concentration of NO3 minus is changed to 0.6 molar, and that of Zn2 plus is changed to 0.85 molar, what's the new cell potential? And I see that the Nernst equation is included there. So E equals E naught minus 0.0592 over N, where N is the number of electrons that are transferred, times the log of Q. Q means that I need a Q expression. And my Q is going to be equal to my products, which I see I have a product of NH4 plus here at 3,2, H2O does not exist in there because it's a pure liquid. My product over here is my Zn2 plus. That goes over my reactants. The Zn does not appear because it's a solid, but I am going to have not only the NO3 minus, but also there's a component for the H plus because that needs to be in there. And of course that H plus is going to be to the 10th power. Now, Is anything else raised to any powers? No, not the way I see it. Okay, awesome. But have we gotten to a place where we could balance this yet? Well, no, we haven't. Because this has 8 electrons in it. There are 8 electrons in that one. And this half reaction up here only has 2. So we would have to multiply this whole thing by 4 to get the same number of electrons, in which case the Zn2 plus is going to be raised to the 4th power. Okay, so that's what that expression looks like. Yay, that was fun. Well, now I know that I've made some changes to those concentrations. So anything that hasn't changed, it's still standard, so it's still 1 molar. Okay, if it's changed, I have a new concentration for it. So the NH4 plus, I don't have a number for. So that's still 1 molar. The Zn2 plus has changed, and that's 0.85. That's to the 4th power. Over the NO3 minus, which is 0.60, times that 1 molar, which is to the 10th power, so it's still a 1. Yay, awesome. That Q is going to go in here. And so when we do that, my E naught is 1.64. We subtract 0.0592 over N, which is 8, times the log of that expression up there. So I have 1.64 minus 0.0592 divided by 8 times the log of 0.85 to the 4th divided by 0. Divided by the 0.60. And when I do that happy math, I get the number as an answer 1.64. And it's a whole bunch of change after that. But we haven't significantly changed this value, not at all. Okay, so that's not unusual, okay, because we changed both of them down relatively similar, so I'm not surprised by that. Okay. Now I have to double a standard reduction potential half reaction to make it work with another half reaction. And actually, we just talked about this. So when we needed to balance the entire equation, we needed to make sure we had the same number of electrons on both sides. So we had to take and multiply this Zn right here times 4. But notice, I did not change that E naught. And that's because the E naught is independent of stoichiometry. And so this means that there is no change since I've done that. Now, based on the cell potential of both the standard and the non-standard cells, are they spontaneous? Well, I have a 1.64 and a 1.64. Okay, awesome. That sign is 0, or greater than 0. So E naught is greater than 0. That means that it's spontaneous. Remember, the sign on E naught determines whether or not it's spontaneous. So it is spontaneous. That means that it goes in the forward direction without any additional work from me once the cell's set up. Okay. Based on the sign of the cell potentials, would you expect the reactions to favor products or reactants? Well, I know that they're spontaneous as written, so I would expect that we'd be looking to form more product. Okay, so this would favor product. Okay, so that's what we're looking at there. Questions, comments, problems? Again, I hope not. I'm going to stop this part of the video, and that way we can get into our actual rate conversations, and I will talk to you in a few minutes.